Okay, today in lesson number 3 in our unit on sound, we're going to talk about breaking the sound barrier because this is something that's has a lot to do with the speed of sound. It has a lot to do with a topic that we're going to discuss in a few lessons, and it kind of creates a nice little base to what we know. There's a lot of really cool videos on YouTube. If you just do a YouTube search for breaking the sound barrier, you can see lots of not only images like this one of the shuttle. You can kind of see this wall of air that's built up around the shuttle as it breaks through the sound barrier. But there's tons of videos where you can see airplanes break the sound barrier, etc., etc. The term sound barrier is used to describe the buildup of sound waves in front of an object when it gets close to the speed of sound. Okay, and we're going to talk about why it happens. So let's do a little bit of a thought experiment. Let's say you're running around basically the football field. It could be our football field. Say you're out there and you're running around at a normal speed, far below the speed of sound. And so as you're running, however, you're doing this experiment. So in the name of science, you let out this boisterous scream as you're running. So you're running at a normal speed, but while you're running, you're also screaming. So basically, let's take a look at the diagram that might look like, right? Because as you run, of course, your sound waves are moving very, very fast. They're moving like 330 meters per second. So they're spreading out away from you very, very quickly. So those sound waves can travel very quickly, and they get away from you. Let's say now that you have superpowers, however, and you're capable at running very close to the speed of sound. So you can run super fast. Now, as you're running around the field and you're letting out this boisterous scream, these sound waves that you're emitting can't get away from you at all because you're running at the same speed as you're emitting them. So what ends up happening is these sound waves bunch up in front of you, and you end up getting this buildup of air pressure in front of you. It's a real buildup of air pressure because remember, sound waves are nothing more than areas of really dense air and areas of really low density air. And so this barrier that builds up of super dense air is called the sound barrier. And it takes a lot of energy to be able to break through that sound barrier. Okay, so we saw in the first diagram, sound waves spread out, move away from you very easily because your speed is so small. But in the second diagram, those waves can't move away from you anymore because of your increased velocity. The buildup of air pressure creates a barrier to your speed, and that's called the sound barrier. So one of the things that has come from the sound barrier is this idea of Mach number. And so when we talk about Mach speed, really we're discussing aircrafts or cars that are getting close to or going faster than the speed of sound. And a different unit is used to describe speed, and that's basically the Mach number. So we can use meters per second to describe speed. We can use kilometers per hour to describe speed. Very often, however, we talk about the Mach number. Mach 1 is defined as the speed of sound at some given air temperature. Any ratio of the speed of sound is expressed in terms of this Mach number. So when we talk about going supersonic, we're talking about any speed that's greater than Mach 1. If you talk about some plane which is supersonic or some car which is supersonic, we're going greater than Mach 1. Subsonic then would be any speed that's less than Mach 1. There's also a term, hypersonic, which is defined as any speed that's greater than Mach 5. Okay, and we can calculate these Mach numbers very, very simply. So let's take a look at an example. What's the Mach number for a plane flying at 839 meters per second in an air temperature of 6 degrees Celsius? Well, if you'll recall from our last unit, the first thing we need to do is we need to figure out what the speed of sound is. So in air temperature at 6 degrees Celsius, the speed of sound, as you can see, once we make our substitution, is 335.6 meters per second. What we do now at this point is that we say the Mach number is equal to the ratio of the speed of our object to the speed of sound. And that's all it is. So when we do this, we take 839 meters per second, we divide it by 335.6. You'll notice that in order to do this successfully, the Mach number needs to be dimensionless. So it means that whatever speed we're talking about, it has to be the same units as the speed of sound. So if you put them both into kilometers per hour, no problem. If you put them both into meters per second, no problem. But they need to be in the same units. And this value would be Mach 2.5. Okay, so we can look at another example. Let's say we've got a fighter jet flying at Mach 3.2. It's in an air temperature of 2 degrees Celsius. What is the plane's speed? So this is the reverse of that example. We start with Mach 3.2, and we have a speed of, or a temperature of 2 degrees Celsius. The speed of sound in this case is 333.2 meters per second. And when we substitute this in, our Mach number is 3.2. The velocity of the object is what we're trying to find. And we come to 1,066.2 meters per second is the plane's speed. So obviously all these objects that we've been talking about in these two examples are flying faster than the speed of sound. So what happens when we break the sound barrier? Well, we get what's called a sonic boom. And I'm not too sure if the audience of this specific screencast are old enough to remember Street Fighter. I don't even know if Street Fighter's still around. When I was a kid, we played Street Fighter on at Hasty Market on the video game machines in Hasty Market, and we played it for hours, and we wasted so many quarters that I really wish that I had those back. But anyways, if you remember Street Fighter, or if you play, I don't know, maybe they've released a new version, but if you remember Street Fighter, then you'll remember Guile, and he's this character who's a major in the U.S. Air Force, and he could move his arms so quickly that he could release a sonic boom, which is not really practical, and there's really no physical significance. However, this is what Guile was able to do. He actually shouted "sonic boom" when he released this sound wave, this shock wave, and it sent his opponents flying backwards. So anyways, that's Guile, and that's basically a sonic boom. There's not very much physics in that, right? There's not very much physics in that. However, the idea and the premise of a sonic boom is that when an object does break the sound barrier, it does leave a wake behind it, a pressure wake behind it, similar to the way that a boat will leave a wake in the water. So if you've ever looked backwards at a boat, and you've kind of seen how the boat sends a wake out, and of course it sends a wave. Well, airplanes do this as well, and they send this huge wake of built-up pressure from the tip of their nose and the tip of their wing, and it's basically a sonic shock wave that is created because all these different waves that have built up in pressure to create the sound barrier now they add together to create one super wave. Okay, so here in the diagram we've got an airplane, and yes, I know this is probably a little bit difficult to draw, but we have this airplane. It's following a path of the dotted line, and we have from the tip of the plane we have one kind of pressure wave that's sent out, and from the wings of the plane we have another kind of pressure that's sent out, and this is emanated, basically it spreads out in 3 dimensions as a cone, but people on the ground, basically the first wave hits them and then the second wave hits them. These are 2 massive pressure waves, and so what they hear are basically 2 really loud booms, or like cracks of lightning. And if you watch a couple of these YouTube videos that have sonic booms, you can hear them. You can hear how loud the sonic boom is. And depending on basically how far the object is away and the conditions of the air, sometimes the shock wave will never reach the ground. But in general, when you go to air shows and when you get these fighter pilots that are going faster than the speed of sound, they'll fly right over top of the crowd and you'll hear 2 really, really good loud sonic booms. If the sonic boom actually does hit the ground, there's a lot of energy associated with these waves. Like, not only can you hear them, but you can feel them because they're strong enough that sometimes they can shatter glass. Sometimes they can shatter glass. Now, this was also the topic, and you can find it on YouTube. This was the topic of a Mythbusters on as to whether or not a sonic boom could actually shatter some glass. And their results are pretty interesting. Their results are, it's really interesting how they set up the experiment. So I would recommend that as well. But basically, in these skyscrapers, years ago when they used to have the Concorde, which was a supersonic jet, and it would fly back and forth from New York to Paris and back and forth. The Concorde, basically, they weren't allowed to go faster than the speed of sound because they didn't want sonic booms over all the skyscrapers in New York City. So, anyways, a little bit of just for interest sake there. But yeah, definitely the Mythbusters video on the sonic boom breaking glass is quite neat.